Good morning, and thank you to the organization for the effort made to celebrate the conference. My name is Nuria Sanchez, and I'm working as a technical researcher at CIEMAT, a Center for Energy, Environment and Technology Research. The purpose of this meeting is to talk about the outdoor thermal comfort approach in summer season for the city of Madrid, and assessing the influence of urban typologies in microclimate and the outdoor thermal sensation. This research is a further step in the influence of the real urban typologies characteristics in the urban microclimate behavior and its impact on the outdoor thermal comfort in cities. The city of Madrid is the case studied, and it's because of the urban complexity and its high summer temperatures associated to a heat stress. One of the detailed urban classification for Madrid is provided by the Statistical Institute of the Community of Madrid. It delimits geographically residential areas in 8 typological sectors, as you can see on the left image. And on the right image, you can see a map of Madrid with the location and details of the meteorological variables monitoring points that are registered through the climatic network of Madrid City Hall. And later, Statistical Institute's urban typology classification has been overlapped. Let me expand on the microclimate characterization of Madrid. Urban distributions, morphology, materials or surfaces shape local climatic variables. However, most of the climatic databases doesn't consider these variations from a micro-level perspective. As I said before, this study analyzed real climatic data of Madrid through the climatic network. A summer representative day has been evaluated because summer season is critical in Madrid in terms of external thermal comfort and worsted by extreme weather events and the urban microclimatic effect. The images on the right are a sample of the distribution maps created using geographical information system tools. Let's now look at the most relevant thermal comfort indices. For this study, we have selected the Universal Thermal Comfort Index, which is independent of a person's characteristics, and we selected this because it's valid in all climates, seasons, and scales. I would like to shift focus now to the main results. Regarding the definition of the urban typologies, there are 2 results I'd like to highlight. The top image represents the mean height of buildings and the representativeness of residential constructions for the Statistical Institute classification. The representativeness of a compacted high-rise typology sums up a total of 34% of buildings. The bottom figure indicates the percentage of the surface that is distributed for public spaces and private zones destined to residential areas. Results reveals that in compacted urban typologies, most of the public surface is occupied by roads and private areas are mostly destined to the built zone. On the contrary, in dispersed urban typologies, there are more green areas in public spaces and private areas have more spaces of pavement and private gardens, and this lasts especially in single-family houses. Moving on now to the characterization of the microclimate behavior, weighted mean values of main meteorological variables have been calculated for the diverse urban zones and using the previous interpolation maps. The graphs on the left show main meteorological values according to the diverse urban typologies. All of them present inverse behaviors of temperature and relative humidity, and in the night it is observed slight differences between urban typologies that cancel out during the day. We can see that wind speed present moderate differences in early morning and the afternoon, and no significant differences were registered in the solar radiation. As I have previously mentioned, the Universal Thermal Comfort Index has been selected for evaluate the outdoor thermal comfort perception. The Sky Helios Pro software is used to define this comfort index. Results are displayed for 2 representative neighborhoods of each urban typology and simulated on a summer representative day. The image on the left shows the comfort index distribution in an example area of the selected 14 neighborhoods. As an example, 5 a.m. and 3 p.m. are chosen times, and this is because they correspond to the lowest and highest comfort index values. The bottom right image represents the hourly mean comfort index behavior considering weighted mean values of the two representative neighborhoods per typology. From 10 p.m. to 10 a.m., all urban classifications are in the category of no thermal stress, and the rest of the day the thermal sensation is moderate stress and strong heat stress. Minimum and maximum comfort index values represented on the top images show that some urban structures modify the previous comfort index behavior. Minimum values attenuate the comfort index curve, and maximum comfort index values reach the category of very strong heat stress during the afternoon. In conclusion, a first approach to study the outdoor thermal comfort in Madrid is done. Universal thermal comfort index values in summer period show no thermal stress at night for all urban building typologies. However, mean thermal sensation at the afternoon is a strong heat stress, reaching very strong thermal stress when considering maximum comfort index values. So consequently, urban planning strategies are needed to reduce the thermal stress and especially forecasted heat waves. Climate adaptation solutions can be started to implement in compacted high-rise neighborhoods, which is a significant building typology of Madrid. Well, I'd like to thank you all for your attention, and if you have any questions or comments, don't hesitate to contact me by mail.